Hello everyone. So let's wait for 4 to 5 minutes. Then we will start this session. Okay. We are waiting for 4 to 5 minutes so that some more people can join. Then we will be starting this session. Okay. So just wait for some time. Okay. I hope that I'm audible to you. So you can reply in the chat box also if you don't want to speak. Just let me know that am I audible to you? Okay. Let us start this session. So let us first let me introduce myself. So my name is Himanshi Singh. I am a research scholar at the Department of Mathematics, IIT Jodhpur, and currently I am pursuing my PhD in broad area of probability and statistics. And I am your TA for the course Essentials of Data Science with R Software 2, Sampling Theory and Linear Regression Analysis. So this course is Professor Shalab is teaching this course on NPTEL portal, and this is our live. So I am taking this live sessions every week on every Monday from 6 to 8 p.m. And this is our last live session. So we will be discussing the content which has been discussed in week 11 lectures, which are there present in the NPTEL portal. Okay, so and so this is the schedule. So we have followed this schedule for the live sessions, and we reached at this uh, 12th live session. So this will be our last live session. So we will be summing up week 12 lectures, and also if there is something which you want to ask, then you may ask. Okay. These are the links. So which is basically, first one is the Google Meet link by which you can join the class. This is the YouTube link by which you can access the recordings of this live sessions, all the previous recordings. So I have uploaded this the recordings on this channel. And third one is the Google Drive link, so where I'm uploading all the R scripts and the presentations which I'm discussing here in these live sessions. Okay. And apart from this, our plan for live session will be, so I will be giving you a brief recap about the topic which has been covered in week 12. Okay, and if there is a need, then I will be show those any commands or whatever we discuss in our. Okay, and then we will do some of the practice examples, and if any doubt is there, then you may ask. Fine. So I hope whosoever has joined, you have completed the week 12 lectures, which are there in the on the SAM portal. Because then only we'll be able to understand, because I will be giving you a brief recap about the topics only. Okay, I will not be going in much detail. Okay. So basically, we were discussing previously, we were discussing about the linear regression. So first we discussed the simple linear regression, then the multiple linear regression. So if we talk about the multiple linear regression, so we were basically considering this model y is equals to beta naught plus beta 1 x1 plus till beta k xk. Okay, where these x1, x2, xk are explanatory variables, or I can say independent variables, and y is the dependent variable, and we are basically fitting this model into a data, and we are finding out the estimates for beta naught, beta 1, beta k. And further we were talking about the what can be the estimators for betas or beta i's, and what is the variance of the estimates. Okay, so we were talking about all those things. Further, we also talked about not only the point estimation, we also discussed the confidence interval estimation, and also we have discussed the hypothesis testing. So when we were discussing the hypothesis testing, then we considered only the individual regression coefficients. So basically, we were considering H naught to be, we have considered like beta I is equals to 0, and H1 to be beta I not equals to 0. So we have basically considered a particular or an individual regression coefficient. Okay, beta I, yeah. But so basically, which tells us the conclusion for it, like if in this case, whatever the methodology is, if we reject H naught, so basically it implies that this, so we are basically rejecting H naught, so this implies that beta I, what for whatever I it is a significant regression coefficient. So corresponding, if there is a, so for example, if you are considering beta 1, then if for beta 1 to be equals to 0, we reject H naught. So basically we are saying that beta 1 is not 0. So basically there is a linear relationship and between y and x1, and it is having a major role. It is significant enough to consider this. Okay, and if we do not reject H naught, that implies that that particular beta I is 0, and we can drop that particular explanatory variable of whose the coefficient of which the coefficient we are talking about. Okay, so that was basically the conclusions. But now, in this class, we will talk about that how we will tackle the problem when we are simultaneously considering the null hypothesis to be like beta 1 from beta naught. If I start, so beta naught is equals to beta 1 is equals to till beta k is equals to 0, and h1 is that beta j is not equals to 0 or at least some j. Okay, so this is basically the hypothesis which what it is interpreting. So we basically interpret from it that if we reject h naught, so that implies that we are rejecting that all beta i's are 0. So what we are accepting that for at least one j there is a linear relationship. So basically there is a linear relationship between y and some xj. Okay, so we can fit that model by skipping other explanatory variables, but for some beta j's, we have some explanatory variables which have a linear relationship between y and those explanatory variables. Okay, so if we reject h naught in this hypothesis, that basically tells us, but it may not tell that for which variable, for which regression coefficient the impact is more, and for which regression coefficient the impact is less. So that we can do by the individual analysis, which we have already done. Okay, so in order to check whether there is a linear relationship or not, we will consider this hypothesis. Okay, so if we reject h naught, then we will say, okay, there is some linear relationship between y and some of the xj's. May not be all, but there is for sure some xj's present which have a linear relationship with y. Okay, so basically this kind of a problem comes under ANOVA, that is called as a analysis of variance. ANOVA is a general term here because we are comparing these beta i's, or we are equating them to 0 and considering this null hypothesis. That's why we are calling it ANOVA. But in other scenarios also, this kind of problem can be called as ANOVA. Okay, so ANOVA is a pretty general term. So here if we consider here if I am considering this model, y is equals to beta 1 plus beta 2 x2 plus till beta k xk. Okay, so there are k minus 1 explanatory variables. Okay, and there are so this is beta 2 beta k, beta 1 beta 2 beta k. These are the regression coefficients, I can say. So this is the intercept term, and others are the coefficients of different explanatory variables. So this is our model. If we consider that, then what we are basically considering the hypothesis. So h naught will be beta 1 is equals to beta 2. Oh, not beta 1. We will consider beta 2 is equals to beta 3 is equals to till is equals to beta k is equals to 0. Okay, we are not considering here the intercept term. We are only considering from beta 2 to beta k equals to 0. This is our null hypothesis, and h1 is beta j or I, you can say whatever you want, is not equals to 0 for at least 1 j. Okay, so this is our hypothesis, the null and the alternative, and we basically want to test this. Now, in order to test this, we want some statistics. So based upon which we can basically give a test. So basically test statistics will be a function of random variable. Whatever observations we have, we will just put onto that statistics. Then we will calculate that statistics, and that statistics will be having some distribution. And on the basis of that distribution, we will have a decision rule, and we will on the basis of that decision rule, we will be deciding that whether we will be accepting h naught or rejecting h naught. So what will be that statistics first? So first let me talk about that. So for that, I have to define some of the terms. So here there is an error term also, so I'm just considering it here. So these are not observations here, I'm considering them as a variable. Okay, so here that's why I've considered this error term also. So we have discussed about sum of squares due to residuals in the previous topics also. So here the sum of squares total is basically divided into two parts, or I can say partitioned into two parts. And there is some mathematics and all those things, and I have this bottom line that sum of squares total is equals to sum of squares due to residuals plus sum of squares due to regression. Okay, so due to regression means these coefficients, sorry, these explanatory variables we are talking about, and residuals is we are talking about this random error. So this is the expression we have, and what are the formulas for that? So for residual, so we can call it as, so in our slides maybe we can call it as SST as a short form. SSE, I'm taking it E because this is because of the error, and SSR, this is because of the regression. Okay, so I will just use this short forms for these terms. Okay, now what are the what is the formulations for this these quantities? So if I talk about SSE, so that is basically I'm talking about the due to residuals. So this we have talked about before also, and the expression for this is, so this is y minus xb transpose to y minus xb. Here we know that x is that matrix, this matrix. So if we have observations here, so in we have this matrix. So here we have, for example, n observations for x2, we have n observations for xk, and similarly we have n observations for other explanatory variables also. That matrix will be this X matrix. This we have discussed already. Okay, the B is the estimate or estimator, which we are getting from the ordinary least square estimation. The process we have already studied. We got this vector as our the what are the estimators for this. Okay, so that is that vector B, and Y is nothing but we also collected the observations for Y also. So that is that vector. Okay, so SSE is this expression. Okay, SS, now we have due to regression. So SSR is, or I can say, I will write first of all SST. Okay, so SS due to total is Y transpose Y minus summation yi whole square divided by n. Here n is the number of observations. Okay, y transpose y, we know all these things. And if we have all the observations, we have everything, then we just put them here and we can find out these values SSE and SST. And we also have this, okay, we also have this relation that SST is equals to SSE plus SSR. So we can calculate SSR from here also. So SSR will be, if we calculated them, then we can calculate by subtracting SST minus SSE. Okay, we can calculate it from here also. Okay, and also this due to regression, so we have explanatory variables. We have k minus 1 explanatory variables. So this SSR is basically partitioned into k minus 1 steps also. That is the regression, that the sum of squares due to x2, ss due to x2 plus ss due to x3 till ss due to xk. Okay, the sum of squares due to different xi's, and which basically come out to be the SSR. Okay, which sums out to be SSR. Okay, so this is the sum of squares for this. Now we'll talk about the degrees of freedom. So you can see here this SSR is basically coming out from the when we are adding how many sum of squares due to xi. So there are k minus 1 xi's, explanatory variables I can say. Degrees of freedom for SSR is k minus 1. Okay, so if we talk about the degrees of freedom, okay, so for SSR it is k minus 1. Okay, let me erase it. Okay, and for this residuals, we have already studied that for the residuals, for the residuals or for because of the errors, the degrees of freedom for SSE is n minus k. Here you have to make sure that here what you are writing is to be k. I am writing k because here I have taken this model. So here this xi, so we have k minus 1 explanatory variables, but here I am taking it to be k. Here in SSR I am taking it to be k minus 1. So you have to make sure that which k you are talking about. You do not have to be confused between that how many explanatory variables. So k is none, k is not number of, it is not number of explanatory variables. Okay, it is not. K is, k minus 1 is the number of explanatory variables. For this model I'm talking about. For this model, k minus 1 is the number of explanatory variables. Okay, so you have to, because in the formulas we will be using all those things, and you have to write it in a correct way. Okay, so this is SSE, and SST will be sum of both of them, and sum of both of them will be n minus 1. Okay, so there is a two relation. So this comes from a theorem, but that is a mathematical aspect or theoretical aspect of it. But the bottom line is that SST is sum of SSE and SSR, and the degrees of freedom also, we are getting the degrees of freedom of SST to be the sum of degrees of freedom of SSE and SSR. Okay, so that is n minus 1. Okay, so this is the these are the some of the quantities. Now we will be now further also we have another quantity, that is mean square. Okay, so mean square is nothing but we talk about this is sum of squares divided by the degrees of freedom. Okay, so if I talk about mean square due to this regression, then it will be sum of square due to regression divided by its degree of freedom. Okay, SSE will be sum of squares due to error or due to residual divided by its degrees of freedom. Similarly for the total one. So here if I write, so I'll write it in a short form MSE. So it will be SSE, and due to errors the degrees of freedom was n minus k. So it is divided by n minus k. MSR, this is because of the regression. So it is SSR divided by, due to regression it was so due to regression it was k minus 1. Yeah. Okay, and MST will be SST divided by n minus 1. Okay, so these are the mean square. Now our statistics, or I can say the test statistics, will be based upon this quantity, these two quantities, this one and this one. Okay, so now in order to test the hypothesis, we have test statistic or F statistic, I can say. Why F statistics? Because this statistics follows F distribution. Okay. So that is equals to the mean square due to regression divided by mean square due to residuals. Okay. So this is the quantity, this is the test statistics we have. Okay, and this follows F distribution with due to regression we have how many degrees of freedom? K minus 1, comma, due to error we have n minus k. So k minus 1 comma n minus k degrees of freedom. Okay, so this will be the test statistics under H naught, under the null. Fine. Now what is our decision rule? So we have already discussed about the p-value. So basically if we do the R code, then we'll get directly the p-value through the code only. So there are two types of two ways to like get the that whether we want to reject or accept H naught. So first one is, so we reject H naught if p-value is less than alpha. So we reject H naught at alpha level of significance, I can say, if p-value is less than alpha. So basically this p-value will be calculated using this statistics only. Okay, and also, or I can say, or we reject H naught if So if I name it as, for example, f, so uh, uh, if f is greater than f alpha k minus 1 comma n minus k. Now what is it? So basically alpha is the level of, so we have f tables, the distribution tables. We have normal table, we have standard normal table, we have chi-square table, we have f distribution table. Okay, so in that table we have like degrees of freedom, like k minus 1 comma n minus k, so whatever the numbers can be. So there are different combinations. We also have different values of alpha in that table. From that table we can compute this value. Now if this value is greater than that particular value for particular k, particular n, then we reject h naught, otherwise we will accept at that level of significance. Okay, so this is the way by which we can find out whether we want to reject h naught or not. So is it fine? Is it fine? Any doubt? Okay, so if there is no doubt, I will just talk about ANOVA table also, basically by, because I will be discussing that in a question. So I'm just telling you in ANOVA table what observations basically we need. So if we talk about ANOVA table, so ANOVA table will be like we will have like regression here. So I'm just, this is my way of giving it. It is not like it is I'm not saying that this will be, or this always will be the things there in the ANOVA table, but what I expect you to give me whenever I'm asking in the question that write the or find out the ANOVA table, then just find out these all things which are there in this table, then that will be fine. Okay, otherwise if there is some question there, they will be specifying that what you need to find, which quantity you need to find. Okay, so it will be the due to regression, due to residuals, and total. So basically we have talked about sum of squares, so we need to find sum of squares. Okay, apart from that we have degrees of freedom. Okay, then mean square. Okay, then f statistic. So this thing only you need to calculate if you are talking about the ANOVA table. Just calculate these things, then that will be your ANOVA table. Okay, whatever it is. Okay, so this will be the sum of squares due to regression. This will be a corresponding degrees of freedom. This will be their ratio, so that will be mean square. F statistics you will be calculating. So there will be only one column. Okay, and similarly for the residuals and similarly for the total. Okay, so this was about the ANOVA thing. So we will be doing some questions on it. Apart from this, we also had the concept of coefficients of determination. So basically, if I have two variables like y and x, then we have correlation coefficient. Okay, we have correlation coefficient. Now why I'm discussing all these formulations here, because so that you guys get a kind of a recap of all the formulations, then whenever we are doing the questions, then you have do not have to like go back to the lectures and see all the things that what were the formulas. That's why to make this kind of a live session complete, I'm just recalling all the things. So this yx, so if I have two variables like y and x, correlation coefficient was there in order to measure that whether there is a linear relationship between x and y and what is the extent of that relationship. Okay, so how much linearly related they are. If we have a larger value of correlation coefficient, so basically that lied between minus 1 and 1. Okay, and if it is more towards one, then we can say that the linear. So basically, it talks about only the linear relationship, nothing else. So we cannot say that non. We cannot say anything about if there is a non-linear relationship between the two variables or not. We are only talking about the linear relationship here. Okay, so if the correlation coefficient is towards one, then we towards one like it is 0.95, then we say that there is a strong linear relationship between the variables y and x, and the relationship is like that if we increase x, the y will also increase. Okay, However, if it is like towards the negative side and it is like minus 0.95, then we can say that okay, the relationship is very strong. But if we increase a particular variable, like if we increase x, then y will decrease. It is in that way. Okay, if coefficient is 0, then we can say that they are not linearly related. Okay, so that was for the two variables, but here we are discussing about the multiple linear regression thing. So what about that? Now for that, the similar kind of methodology or similar kind of formulation is there, a similar kind of quantity is there, which basically measures the linear relationship between multiple between a independent sorry between a dependent and a more than one independent variables. Okay, so that is called coefficient of determination, which basically is defined as r square, and which is given by, so this have a formula. So let me get that formula. So yeah, so in like if you have observations, then this is a very large formula, like x transpose x inverse x transpose y divided by y transpose y. And if you have like values of regression, the sum of squares due to regression, sum of squares due to total, and sum of square due to residuals, then there is also formula, that is ss regression divided by ss total. Okay, and which is equals to 1 minus ss residuals divided by ss total. So this is kind of a different formulation, whatever you have in your hand, by making use of. So if you do not have these quantities, then either you can calculate these quantities by the observations, then calculate, or just put all the values in this formula. So here you can see that we have to find out the inverse of this matrix, and we have to find out this multiplication, we have to find out this multiplication and then divide that quantity by this. So this is a very large calculation. If we have like 4 or 5 explanatory variables, and this will be very messy. But if you know the SS, the sum of squares due to regression, sum of square due to total, then you can just directly calculate the ratio and find out r square. Okay, now this r square have some drawbacks. Like if we increase the explanatory variables, then this r, the value of r square will also increase. So if whether the variable is relevant or not, it will increase. So it will give us a picture that okay, increasing a variable, it is giving more r square. So okay, the model is getting better. However, in reality, it is not getting better. So in order to tackle such kind of things, this adjusted r square was given. So adjusted r square, so which was basically denoted by r bar square. And the for this there is a formulation, that is 1 minus ssres divided by n minus k divided by ss total divided by n minus 1, which can also be calculated using 1 minus n minus 1 upon n minus k into r square. Okay, now this also have some drawback. This is basically, in order to tackle some of the problems, we are again having some problems that this can be negative. This can be negative, which is a very like weird thing, because no interpretation can be there if it is negative. Okay, so based upon the understanding, we have to see that whether we have to go with r square or r bar square, or both, or none of them. So that is the thing. So this is basically the formula. So if we arrive at some of the question where we are using this formulas for r square and r bar square, we'll be using this. Okay, fine. So this was about the how to like measure the adequacy of the model. So basically, if r square is more towards 1, so this also basically so yeah, I forgot to mention. So r square here, this r square is between 0 and 1. Okay, and if it is towards 1, like it is 0.95, and we say okay, all the variables are like so the model is very good, and the all the explanatory variables having some part to play, and it is a very good model. Every variable is having a good contribution, and there is a good linear relationship between the dependent and the independent variables. Okay, so this is about, and if r square is 0, obviously the fit is very poor, and maybe there is no linear relationship between the two variables or between these multiple variables with the dependent variable. Okay, here we are only talking about the relationship between y and the group x1, x2, xk. We are not talking about, or I can say, we are not talking about the relationship between these variables. We are only talking about between this and this. Okay, fine. So this was about this, and yeah, so this was about the fit, goodness of fit I can measure using this r square. Okay, now we have commands. So if we talk about the commands, so basically we have discussed about the ANOVA table, we have discussed about the r square adjusted r square. So in the previous lectures, we have discussed about this lm command. So if I have, for example, so let me write first. So for example, I have this y is equals to, for example, b1, beta 1, beta 2, x2 till beta k. So let us consider it to be only two explanatory variables, that is beta 3, x3. Okay, so if this is a model, then I'll just store the observations in the variable x2. I will store observations in and x3, and I will store the observations in the variable y, or a data vector y in R. Okay, so if I store them, then in order to fit a model, linear model, in order to find out, okay, what beta 1 hat is, beta 2 hat is, beta 3 hat is, we'll just use this command. We have used already that lm, this y tilde x2 plus x3. So x2 plus x3 depends upon in which data vector you have put the value, where you have stored the values. Okay, so this is lm this. If you use the summary here, summary lm this thing, if you use this command, okay, if you use this command, then we have also discussed this, that this command will give us a lot of informations. So basically we have already discussed that it will give us the beta I hats, basically the estimates of this. Okay, it will also give us the ssres, the residuals. It will also give us the standard error due to this xi's, this x2 and x3. Okay, which we have already talked about in the previous lectures. Okay, apart from this, it will give us the p-value. It will give us the value of the statistics for the individual for individual tests. It will also give us the test statistics and the corresponding p-value. Further, what we have not discussed, this command will also give us the value of f statistics. Okay, f statistics will also be given, and also it will also give us the value of r square. It will also give us the value of r bar square. Okay, and also it will give the corresponding p-value, on the basis of which we can just give, okay, fine, that this is the p-value, and the basis of which we can decide that our null is rejected or not. Okay, and also for the ANOVA thing, if you want to find out the ANOVA table, the value of the value of the sum of squares due to particular, the like x1, x2, x3, the SSRES, and also the SS for the total, the sum of square for the total, the degrees of freedom, and all those things. If you want to find out, then this command ANOVA, okay, and this same lm y tilde x2 plus x3, this command will give you. Okay, so this command will give you that. I hope this is clear. If there is any doubt, then you may ask. Okay, so if there is no doubt, then I'll move forward. Okay, so before moving, I will discuss this thing in R first. Okay, so here I have this observation. So here I've considered three explanatory variables, and I've stored some values, some of the observations, and in the dependent variable also I have stored these values, and they are 10 values. We have n to be 10. Okay, so these are the values I have stored here. So let me run it. Okay, so I have not shared actually. Wait. Yeah. So in R, I have I've stored these values. Okay. So first of all, let me just wait a minute. Okay, so here I have this like a script, and here I have three explanatory variable x1, x2, x3, and y is a dependent variable, and x1, x2, x3 are independent variables. I have stored some observations here, and here this if I run it, so okay, these are stored here. Now if I do the lm y tilde x1, x2, x3, so it will basically give me the fitted model. Okay, so let me see that what is that model here. So the here model is this. So here I'm getting the estimate for the intercept term to be 19.57. The coefficient of x1, that is the beta 1, I can say, is 1.23. Coefficient of x2 is minus 0.607, and the coefficient of x3 to be 1.1036. Okay, so this is basically the fitted model, fitted linear regression model, multiple linear regression model. Okay, now if I run the summary command here, then I get this these many values. So here you can see here the residuals of basically for each of the exercise there will be residuals. So the information for those residuals are given. So basically E1, E2, many EIs will be there. So that residual informations are given. Apart from that, we have the information about the coefficient. So that is a major one. So here we have this intercept to be 19.57, the coefficient of x1, x2, x3 here, and the corresponding standard error. So this we have discussed already in the previous slides. We have this, the value of the test statistics. So basically we considered there, when we had considered the hypothesis testing, the distribution of the test statistics was the student t distribution. So the t distribution, we got the values of the statistics, and here it is called as a t value here. So these are the value of the test statistics, and these are the p values here. Okay, so here these are the p values, and if I want to do individual tests, okay, so here for the second one you can see that the p value is 0.002, which is very less. So if I consider 5% level of significance, so it is less than 0.5. In fact, if I consider 1% level of significance, then it is less than 0.01 also. So I can say that at 1% level of significance, here for this one, the p-value is less than the alpha, that is 0.01. That's why we'll reject H naught. So if I consider about the single individual, if I consider that beta 1 is equals to 0, if I consider only this hypothesis, then for that I will reject the null hypothesis. Here I'm talking about the individual thing which we have discussed already in the previous lectures. Okay, so for this, but however, for other ones, if I consider 1% level of significance, we will not be rejecting H naught. Okay, fine. So here we apart from this thing, also what we got, the residual standard error, that is 0.6837. This is SSRES, RES on the 6 degrees of freedom. Okay, why 6 degrees of freedom? Because we have three explanatory variables. Okay, we have three regression coefficients, and one is the intercept one, so that's why it is 4. So 10 minus 4, that is n minus k, so that is 6 degrees of freedom. Okay, also we got this multiple r squared, that is 0.9932, which we have discussed now, and adjusted r squared, that is 0.9897, which also we have discussed now, and f statistics, the value of f statistics is given, okay, on this k minus 1 and n minus k degrees of freedom, and the p value is also given, which is also very less. So basically, if the p value is very less, so basically we'll reject H naught if p value is less than alpha. Okay, so here it is saying that we will reject H naught. Reject H naught means that at least one of the beta j is there, which is not 0. So basically, there is a linear relationship. This basically is saying. Now, which is a significant, which is not significant, hypothesis will tell. Apart from that, also we have some more technique. Okay, I will be discussing that later. Now, before that, let me discuss about this ANOVA. So how we ANOVA table. So if I write this ANOVA model means this LM, this same thing only. So ANOVA model, if I write it, so here I'm getting ANOVA table. Here, these are the variables, explanatory variables x1, x2, x3, the degrees of freedom. So for each explanatory variable, the degrees of freedom will be 1, 1, 1. And if we add it, so it will be 3. So that will be, okay, will be for the regression, but individually it will be 1, 1, 1. The sum of squares due to x1, due to x2, due to x3, if we add all these three, that will be the sum of square due to regression. Okay, mean square will be this one, this one. So this will basically be the division of this thing. So that is same only. F value will be the value of the whatever we have discussed. That's SS regression divided by the uh, not SS regression, the regression, the mean square due to regression divided by the mean square due to the residuals. Here the degrees of freedom for the residuals is 6, the sum of square is 2.80, and the mean square is 0.47. So basically the F value, the final F value here, the final F value will be, if I talk about the F statistics we talked about. So basically we'll add this mean sum square. So we'll calculate the mean sum square due to the regression and divide it by this the mean square due to residual 0.47, and we get the F value. Okay, here the P value, here we have 3 different P values for different variables. Okay, and the final P value we got here, if we talk about. So calculating both of them are different. Okay. Okay, so this is for this ANOVA and the R square and the adjusted R square. Okay, so I hope this is clear. If there is any doubt, then you may ask. Just give me a minute. Just tell me if there is any doubt. I'm just giving you 1 minute. Okay, so if there is no doubt, then I'll move forward for another thing. This lasso regression, the variable selection due to using the lasso regression. So basically, I have, for example, I've discussed that okay, fine, I'm considering this hypothesis this to be 0 under the alternative that some beta j is not 0. Okay, so here this I'm considering. So it is basically giving me the idea, okay, that whether there is a linear relationship or not. If I got, okay, I have rejected H naught and I got the idea that I have to reject the H naught, fine, so there is a linear relationship. Now if I have more beta j's, okay, then the calculation and all those things are very complex. Okay, so more number of regression coefficients will increase the complexity. Okay, complexity as in like in calculations, computations, and all those things will become very complex. Okay, so because there can be variables which is affecting less, there can be variable which is affecting more. Now we have to decide which variable we want to consider and which variable we do not want to consider. Okay, so there may be some variables which are not that important to consider in our model, so there is a chance that we can skip them. Okay, so there are many methods by which we can find out. There are many packages in R also, which by which we can find out, okay, for which beta j we can skip particular beta j for which of the values. Okay, so basically what is the methodology for the, if I consider the lasso regression, so in a broad sense, in a theoretical aspect, if I talk about, so basically we find out the beta caps. Okay, beta caps means we are finding out the estimates. Okay, here it may not be necessary that we are always be able to find out the ordinary least square estimators. Okay, and also if it is a possibility, then there are other methods also by which we can find out the estimates. Okay, so here what how we are finding out the beta hat, we are basically minimizing argument minimum beta in rk. Okay, we are minimizing summation yi minus xi transpose beta whole square I going from 1 to n plus lambda summation mod of beta j, okay, j going from 1 to k. So basically we are minimizing this quantity. Okay, now just suppose lambda is 0. Now if lambda is 0, this term will be gone. Okay, now this, if this term is gone, then basically what we are doing, we are minimizing the summation of yi minus xi transpose beta whole square, so which is basically the method of the least square estimation, which we have discussed already. So if lambda is 0, basically it means that we are finding out the least square estimators. Okay, now what is the role of to introduce this lambda? So basically if we introduce this lambda, then there is a methodology, or there is a explanation, and there is a mathematical theoretical proofs, or the construction of this particular method is in such a way that if the values of lambda is higher, then it will make more of the coefficients 0. Okay, if this value is very much lower, then so basically we want to find out a way by which we can know that, okay, fine, these are the variables we can skip, and these are the variables we have to uh, take with us. If there is a complexity, there is a very much complexity in the model. Okay, so basically here we have to use the value of the lambda in a hit and by a hit and trial kind of a method, so that I can input a particular lambda, find out the beta hats, input different lambda, find out the beta hats, basically gives us the values of beta 2 hat, beta 3 hat, beta k hat, and whichever beta hat is near to, very near to 0, we can skip that. We can skip that particular explanatory variables. Okay, so if the value of lambda is very large, then more of the beta hats will be 0. Okay, so basically we want to reach till that point where all the variables are also not 0, and all the variables are also not equal to non-zero quantity. So we have to reach to that point where there is a balance. Okay, so basically that is the methodology. We'll change the values of lambda, and we can get the different estimates, and we can decide further that which lambda we want to keep and which estimate we want to keep, which explanatory variable we want to keep, and do the further analysis. Okay, so this is the basically the background for the lasso, the variable selection due to the lasso regression. So this is the methodology. Okay, and here also there are different methods in the mathematical things by which we can find out the values of beta hats. Okay, now this particular thing is can be used in R also. We can also use a particular code in R in order to find out the coefficients. However, in the lecture, I've noticed that this lasso package. So here I have taken the screenshot only. Here this IILS, so this IILASSO. So this was a package which was basically downloaded, and all the things were done using this package actually. But when I tried installing it, it was not present actually on the CRAN website. So till my knowledge, I do not know whether it is like fully correct or not. Till my knowledge, I don't think that this package is available now. Okay, so maybe there may be questions in exams which is dependent on this particular slides in the way by which the lasso is like this library II lasso and all these things are working. So that's why I'm explaining it here only. However, for a practical use, for your personal practical use, I will give you a different package, okay, a different command by which you can do the similar kind of thing using a different package. Okay, is that fine? Okay, so basically here, let me explain this first of all by the screenshot only, because I will not be able to run it there in R. So this is basically just install this package by using the install.packages and just call the library IILASSO, which we are doing from the day one. Apart from that, this some variables are stored, some observations are stored in these variables: yield, ferti, seed. There are like 6 variables here. Okay, and there is a dependent variable also. The observations for that also is yield is the basically the dependent variable, this one, and others are the independent variables, and there are the 10 observations for each of the variable. Okay, now for one of for both the for the this by the dependent variable, the data is entered basically, and this is basically converted into a matrix form, and x is basically the x1 x2 x is different explanatory variables, and it is also converted into the matrix form in this way. Okay, this is all we have done like in a basic R course. So this is the matrix now for the independent variable, and this is for the dependent variable. So these are basically the observations. Now further, what we have to do, we have to use this command, basically lasso, LASSO. Let me zoom it a little. So yeah, so this is LASSO x comma y. So basically x here is the explanatory variables, the matrix, and y is the dependent variable. Family to be Gaussian. Okay, and here this lambda dot min dot ratio to be this. So basically this is the ratio between the values of the lambda. So that should be like minimum should be this. So it cannot go uh, less than this particular quantity. And lambda to be 5 for how many values of lambda you want to calculate the coefficients. Okay, and lambda equals to null, so basically it will take the values of the lambda by itself, because you are not giving the value. If you want to give the value, then you just give the value here, a particular value of lambda. Okay. So this is the basically the uh, code for it, and what basically we got using this code. So if I write this command dollar beta standard, so we will get this matrix. So what this matrix basically represents, here there is a matrix. Now here these are nothing but the coefficients only. So these are coefficients, all of them. So this is for a particular lambda, this is for a particular lambda, this is for the particular lambda, this is, and this is. So you can see here you have how many independent variables. We have 1, 2, 3, 4, 5, 6. We have 6 independent variables. Okay, x1, x2 till x6. So we have beta 1 head, beta 2 head, beta 3 head, beta 4 head, beta 5 head, and beta 6 head. So those are only these variables. So beta 1 head, beta 2 head, beta 3 head, beta 4 head, beta 5 head, beta 6 head. But this particular column is corresponding to a particular lambda. Okay, so if you write this whole command dollar lambda, then you get these values. Okay, so basically what it is saying, that this is a value of lambda, that is 5.6, and corresponding to them, these are the value of the estimates of the coefficients. That is beta 1 hat. We are not talking about the intercept here, we are only talking about the coefficients of the explanatory variables, that is xi. So that is beta 1 hat, beta 2 hat, beta 3 hat, all are 0. You can say here lambda value is large, and all the coefficients are 0. So as the value decreases, so here it is taken to be 0.56. So value of lambda to be 0.56, then we get these coefficients. These are the coefficients. If we take 0.056, then these are the coefficients. If we take to be 0.0056, these, and if we take this to be this. But here the it is written dollar beta underscore standard. Standard means that we are talking about standardized data. We are here, original data is not considered, standardized data is considered. Okay, what about the original data? So if we write directly only this command dollar beta, not beta underscore standard, only beta. Okay, dollar beta if we write, then we get this table again. So here again, this is for the lambda 5.6, this is for the 0.56, it is 0.056, this is 0.0056, this is corresponding to this value 0.00056. Okay, here in this thing you can see that at the first, when the value is 5.6, all the coefficients are 0, so we will be not considering because all are 0, all the coefficients are 0. Okay, however, for the second one also you can see that the all three, the fourth, fifth, sixth are very near to 0. Okay, and this one, these are reasonable, the 0.6, 0.61, 0.59, but then also they are not that far away from 0. But in the third one you can see that this, the first one is 1.26, 1.55, 0.56, and these are very near to 0. So what we can consider this one, okay, based upon our understanding, we can consider this one, and what we can do, we can neglect the fourth, fifth, sixth explanatory variable. Okay, we'll just consider first, second, and third explanatory variables, and the coefficients for that model, the coefficient will be 1.26 and 1.55 and 0.56. Okay, now what will be the intercept term? So intercept will be, if you write this command $a naught, so this will give you the intercept terms for each lambda. Now if you are considering lambda third quantity, that is 0.056, then for that intercept term will be 20.0753. Okay, so if you want to do, okay, so here for this particular thing we can consider this third one. Okay, and here what the model will be, so that is 1.2641 x1 plus 1.554 x2 plus 0.565 x3. Okay, and here the intercept term will be this third one, 20.07. So this fitted model we can consider and do the further analysis. Okay, so this is the output for this. Now further, let me give you a different package also. If you if you want to do something similar to it, then alternatively I can give a different package called this LARS. So first of all, you have to install that package. So that is install dot packages LARS. Okay, so if you run it, just wait a minute. So here I am installing this package LARS. So in the left hand side is getting installed. Okay, so it is installed now. I'll just call this package LARS. It is loaded. Okay, now what I will do, I'll just find out this value of, so basically I want to store this data x1, x2, x3. The dependent variable, I'll just use the command cbind. Okay, so my data will be like this. So it is a kind of a matrix format. Okay, now further I have already my data, the data dependent variable to be y, and independent variable I have stored is kind of a matrix format. You can also use the command matrix also here. Further, I will just use this command LARS x comma y type is equals to lasso here. Okay, and I'll just find out and just store those values in fit. Okay, so here I've stored these value. Now if I write fit dollar beta, so it will basically give us the values of the estimates. So here you can see, here I again got this matrix kind of thing. Now here you can see that this first row, second row, third row, the zeroth row we will be not be considering here. Here this will be not considering. So this is first row, second row, third row. So these are the basically coefficients. Okay, here in the first one, basically we do not know further that what is the lambdas are considered. So let us first see that fit dollar lambda will give us what. So these are the values of the lambdas. Okay, so Here, these are the values of the lambda. And here you can see that for this one, you can see that the first one is 0, the coefficient, the second one is 0.52, third one is 1.103. So this we can consider because there is 1 0 here, and we can just skip the first variable, and the first variable we can skip and consider these two variables and just do the analysis. This is a kind of a similar thing that lasso provide, but there are many differences. The output may be different for the same data for both the commands, because the theoretical foundation for both the packages, for both the models may be different, the techniques may be different, the way of calculating the things may be different. But I am just giving you an alternative when you want to do a practical use, and you also have to study more about it if you want to do it literally in your research or something like that. Okay, so I'm just giving you an overview that how, what about, like, apart from this also what we can use, because this isn't working at least in my laptop. And also I have searched it for the CRAN website, and it shows that it is not available there, because this package may be a little older package, and maybe it is like removed from the website. Okay, so if there is any doubt, then you may ask. Otherwise, I'll just move towards the questions. We have simple questions, some 4 or 5 questions. We'll just discuss that. Then we'll end this session. So just let me know if there is some doubt. Let's share this window. So just let me know if there is some doubt. Okay. Okay, so let me discuss this question. So these are simple questions, not that hard and fast. If we have discussed all those things, then it is easy to discuss these questions. Okay. So just read this first question. So basically it is saying that consider this model. So here we can see that there are three coefficients, beta 1, beta 2, beta 1, beta 2, and so just actually I don't know that what will be the pattern, because I am not the one who is setting the exam. But according to my knowledge, you just ask the same question on that Q&A portal also, where there is an NPTEL portal. There is a thing where you can post your queries, you can post your questions. Just write this thing again there, and just ask for there, because they are the people who are basically making all these things. But according to me, um, you have seen the assignments. Okay, just think about whenever you are solving the assignments, just think about that you do not have R, and just solve those assignments. When you do not have R, you just do the things manually. Okay, because if you have R, then what is the use to have a theoretical knowledge? You'll just write the code and find out the output. Okay, so R will not be available. That I think also R will not be available. But you have to. That's why you have to have a theoretical knowledge that how the things are working in R. Basically, what is happening at the back end. Okay, so just read the things that how the codes are working, not that what is the output. Okay, so yeah. So that's why in the lectures also, wherever I have discussed in the live sessions also, I have majorly focused on the manual thinking. Whenever I'm solving a question also, I have not solved the question directly on R. I have just solved that question first manually, okay, by my hand here doing all the calculation, and then I have solved the question on R. Why? Because there are some questions, like whenever you are what you want to calculate, like for example here in this question there is a calculation for SSE. Now this calculation can be very messy. Like we can have a 4 cross 4 matrix, 5 cross 5 matrix. We cannot find out the inverse of that matrix, and that much calculation will not be there in exam also. So that calculations I'm just skipping. Apart from that, if there is some calculation, I'm doing all the calculation. Why? Because I want you people to know that basically how the codes are working. Okay, so that's why the major reason, in order to, like, I'm like having all the slides in, like I'm giving you the recap and all those things. The major reason in order to like giving the recap and all those things is that you should learn that how all the programs, all the things are working in R. Okay, so not only like I'm just writing the commands in R and I'm just giving you the output. Okay, this is the output and this is the meaning and all those things. Okay, so I hope that you should follow this thing. Then I think it will be fine. And also just ask the same question there. Then just see that what the answers, because I do not have any idea about how the question papers come, because the exam is like on a different level. We do not know anything about the examination. Okay, so I hope this is clear. Yeah, so we'll move for this question. Uh, Yeah, so this is the question where I'm considering this model where we have three coefficients beta 1, beta 2, beta 3, and we have two explanatory variables x2 and x3. Okay, now here this SSE is given, that is due to residuals, SSR is given, that is due to regression. Sum of squares for 10 observations means n is 10. Here I want to construct the unavoidable. Okay, so what we have, I have n is equals to 10, SSE is with me, SSE is 20, SSR is 80. Okay, now I want to find out that what are the values in the ANOVA table. So first of all, let me make the ANOVA table. So the ANOVA table will be like, here it will be the to do regression, okay, due to residuals and due to, and this is the total. Okay, here I will get the sum of squares, degrees of freedom, mean square, F statistic. Okay, now sum of square due to regression, is it given? Due to regression it is given 80. So here I am writing it to be 80. Due to residuals it is given to be 20. Okay, and what is given, that n is 10. Fine. Now n is 10. Now what is k? Now what is k? K was the so k minus 1. If I considered my model, then k minus 1 was the number of explanatory variables. Explanatory variables. Here also I have considered the model in the same way. Here I have started from x2, ended with x3. There is no x1 here. Okay, so just make sure that you are using the same model. Fine. So so this is k minus 1. So here k minus 1. So number of explanatory variables are, two explanatory variables are there. So this is 2. So k will be 3. Our k will be 3. Okay, so which we can see also that x2, x3, 3 till 3 it is going. So k is 3. Okay, n is 10. Okay, what is the degrees of freedom for the regression term? So that is, as I've already discussed, what was it? So the degrees of freedom. So for the residuals, as we have already discussed, that it was n minus k, but for the regression we had, so that is equals to the number of explanatory variable only. Okay, so that is k minus 1. So this is k minus 1 for the regression. So which is k minus 1 is 2. And for the residuals, it is n minus k. So which is n is 10, k is 3, 7. Mean square will be the ratio. So this is 80 by 2, so that is 40. This is 20 by 7. Okay. F statistics or total also. Total is sum of squares. For total is 100. This will be the addition. Okay. And the degrees of freedom will be n minus 1. And n minus 1 is what? 10 minus 1, that is 9. And you sum this is also 9. Okay. And the mean square, this is the division only, 100. F statistics, it basically depends on these two terms. That will be this ratio of these two terms. That is 40 upon 20 divided by 7. So it will be multiplied by 7. So it is, so this 2 times and this is 14. So value of the F statistics will be 14. So it was a simple question. You just have to make the ANOVA table and you have to find out these values. I hope this is clear. There is nothing much in this. Is there any doubt for this question? Okay, so if there is no doubt, then we'll move forward. So here the things are given already. So regression, error, total, the sum of squares are given. Basically the SSR is given, SSE is given. Okay, the degrees of freedoms are given. Now I have to find out the mean square uh, for the regression, for the error, and also the F statistics. So this is also simple. There is nothing much in it. So total, if I want to find out, I will just add them. So it will be 120 plus 30. So that will be the SS total. So the SS total will be 120 plus 30. So that will give me 150. Okay, so degrees of freedom are given for all of them. Mean square for the regression, if I want to find out, so it will be the ratio, the mean square, the sum of square into regression divided by the degrees of freedom. Okay, so this quantity will be 120 divided by 2. So it will be 60. And also if I talk about the error term, so what it will be? So just answer this at least. The mean square due to error term, what it will be? This quantity here. The next question mark. What this quantity will be? The mean square into error. So it is basically working in the same way now, because we are talking about the mean square. So it is basically the ratio between the sum of squares and degrees of freedom. So if I talk about the regression, so it will be 120 by 2, because we are talking about the regression. Now if I talk about the error term, so for that sum of square is 30, the degrees of freedom is 12. So it will be ratio only, no? So it will be the ratio only, so it will come in decimals. Okay. Now what will be the F statistics? So F statistics will be their ratio. This divided by this. So it will be 60 divided by 30 divided by 12. So 30 and it is 12 here. So what that quantity will be? It is 24. Okay, so now by from this regression, this ANOVA table, we can also conclude that what is basically the model. Okay, if I talk about the regression, so basically if I talk about regression, the degrees of freedom is k minus 1 basically. So k minus 1 here is 2 because this is the degrees of freedom. So for the regression it is k minus 1. So this implies that k is 3. Also, this due to the error term, the degrees of freedom is due to the error, degrees of freedom due to the error is n minus k. So uh, that is 12 here. So this is 12 and k is 3. So k is 3. So it is 15. So basically, it is telling us that our model is like there are how many explanatory variables? There are two explanatory variables. Okay, two explanatory variables means x2 and x3 explanatory variables we have. Beta 3 here, beta 2 here, plus beta 1 here. So this is our model. Okay, and we have done all the calculation for this SSRES and SSE and all these calculation or all these analysis on how many observations? 15 observations. By these values, we can also conclude that. So here in this question, model was not given, but by the information which are given here and by the formulations we have discussed, we can find out that okay, what is the basically model and how many explanatory variables we have, how many coefficients we have, and how many observations are considered. So I hope this is fine. If there is any doubt or something, then please just let me know. Otherwise, I'll move. Okay, so I'll move forward for the next question. Okay, here it is asked that consider the model as in question 1. So basically, let's see first what is the model in question 1. So here we have two explanatory variables. Okay, so let us write that model. Y to be equals to beta 1 plus beta 2x2 plus beta 3x3. So this is the model. The coefficients of determination is 0.75. Now, what is the coefficient of determination? We have discussed already r square. So that is 0.75. N is given to be 50, given, so our number of observations are 15. Okay. SS total is given. So sum of square due to total is given as to be 200. Now I have this quantity, I have r square, I have sum of square due to total, I have n to be 15. Now I want to find the quantities in ANOVA table. So basically I want to make the ANOVA table. So for the ANOVA table, I need the sum of square due to residuals, sum of square due to regression. I need degrees of freedom. I need I need the mean square. Okay, I need the F statistic. Fine. So you can see here r square. Now by the formula of r square, can I get, because I have SS total, so I know that SS total is equals to SSR plus SSE. I know this quantity, but I don't know both of them. So now how to get both of them? Is there any formulation in R square by which I can get any one of them? If I get any one of them, I can get the other one because I already know SST. Okay. So what is the formula for r square? Let us write first. So basically we had r square, we discussed r square to be SS regression divided by SS total. Okay. So which implies that SS regression is r square into SS total. So SS regression will be r square is 0.75 and SS total is 200. So this quantity will be 75 multiplied by 2. I think it will be 150. So it will be 150. Now we know SSR. Now I want to know what is the SSE due to the residuals. So that is due to the errors. So we know that SST is equals to SSR plus SSE. Okay. And SST is 200, which is equals to 150 plus SSE. Now due to errors, it will be the subtraction. So SSE will be 200 minus 150. That will be 50. Okay, now let's make the table. So it is due to the regression, residuals, total. This is sum of squares. This is degree of freedom. This is mean square. And this is F statistic. Due to regression, we have to be 150. Due to residuals, we have due to residuals we have calculated to be 50, and total we have given, it was given to be 200. Now if we talk about degrees of freedom, so we have k to be equals to 3. Okay, and explanatory variables are 2. Okay, so degrees of freedom for regression is k minus 1, that is 2. That is number of the explanatory variables, which is 2. Okay, for residuals, it is n minus k. N is, how much n was given? To be 15. N is 15. K is 3. K minus 1 is 2. That's why degrees of freedom here it is 2. K is 3. N minus k is 12. It will be 12. For the total, the degrees of freedom is n minus 1. That is 15 minus 1. That is 14, which is total of this also. It is 14. Okay, fine. Now the mean square will be the division. If I divide them, so mean square will be 150 divided by 2. So it will be 75. 50 divided by 12. Okay, and 200 divided by 14. Okay, now F statistic will be this ratio. So that is 75 divided by 50 is at 12. Okay, so this quantity will be 75 multiplied by 12 divided by 50. So that is 18. So this will be our ANOVA table. So here we only knew about the R square and the SST. Okay, and also we know the number of observations. Now from this, by using the formulas and all those things, we find out the sum of squares due to residuals, which sum of squares due to errors, sorry, the residuals and the regression also. And further we calculate the degrees of freedom, and finally calculated the F statistics. Is it fine? Is it fine? Okay, so if there is no doubt, then I'll move forward. So this will be our final question for the course, I think I can say, because this is our last live session. We have no more live sessions. Okay, so this is the question where it is asked that for some linear regression model, multiple linear regression model with 3 explanatory variables. So basically, first write the model. There are 3 explanatory variables, means that y is equals to beta 1 plus beta plus beta 2 x2 plus beta 3 x3 plus beta 4 x4, because we need 3 explanatory variables. Okay, so this one, the sum of squares due to residuals is 60. So basically SSE is 60. Okay, when 25 observations are considered, so basically n is equals to 25. Further, SST is 200. So basically sum of squares total is 200. Then find the coefficients of determination and adjusted coefficients of determination. So that is basically we want to find out r square first. And we already know the formula for r square. So we know that it is, we have two formulations. One is SSR divided by SST, but we do not have SSR here. And other one is 1 minus SSE divided by SST. So obviously we'll use this because we do not have SSR with us. Okay, so this is r square is equals to 1 minus SSE by SST. Okay, so this is 1 minus what is SSE, that is 60, divided by what is SST, we have 200. So this is 200 minus 60 divided by 200. So this is 140 by 200. This is 0.7. So this is the value of r square. Now adjusted r square. So we represent it by r bar square. Okay, so the value for this was 1 minus SS. So it was 1 minus SS, I think, regression. Okay. Okay. We had adjusted r square 1 minus SSE divided by n minus k divided by SST divided by n minus 1. This was the formula. Or in place of that, we can also write it as, okay, wait a minute, actually it, yeah, we can write it like this. I will just cross check the formula first. So here, yeah. Just give me a minute. I had a confusion. Yeah, actually I have written one thing wrong here. Here it will be 1 minus r square actually. Here it will be 1. Because obviously if you reciprocate it, it will be n minus 1 by n minus k. And here it will be SSRES by SS total. And SSRES by SS total is nothing but 1 minus r square. It is not r square. So it will be 1 minus r square. So yeah, this is a mistake there. Yeah, otherwise it is fine. Because you can see here also SSRES by SS total, it is 1 minus r square. So here also it will be 1 minus r square because this is the same ratio. Okay, so yeah, I'll write it there. So this, yeah, so this is SSE and divided by this thing, and this can also, we can also write it as 1 minus n minus 1 by n minus k, and here it is 1 minus r square. Okay, you know all the values, these values are also known. We also know the r square. You can compute the way you want. So let me compute it using the r square. So it will be 1 minus n minus 1 is what? Here n is 25. So it is 24 divided by n minus k. Okay, so n minus k. So 25. So k is what? Here k is 4 because there are 3 exponential variables. So that is k minus 1 is 3. So k is 4. So it will be 4. This is 4 here. N, sorry, not 4. N minus k. It is 25 minus 4. N minus k is here. 1 minus r square. So 1 minus 0.7. So it is 24 divided by, here it is 21 and here it is 0.3. Okay. So it is 1 minus, or I can say 70 minus minus 24 divided by 70. So that will be what? 6 46 by 70. It is 0.657. So you can see here the r square was 0.7 and the adjusted r square is 0.65. So there is a little difference between the two. But yeah, so this is the thing about the r square and r bar square. The thing about the lasso, I've explained it already. And this is about the ANOVA and the r square and adjusted r square. So these are the only questions I will be discussing for today. Okay, and yeah, the recording for the today's session I will be uploading it on the YouTube, so you may access it from there. And also there are recordings for each live session. You can access it from there. The presentations and the R scripts will be added to the Google Drive. And yeah, the deadline for your this assignment 12 is 15th of April. So just submit it before that. Okay. Now, if there is some doubt, then you may ask. Is there any doubt or anything? This is our last live session. I think now you will be having your exam only directly. So any one of you have registered for the exam? So you have registered for the exam? Okay. So when is the exam? Is the date like they have given a date or it is not given yet? So when is your exam? Oh, it's on 19th of April. So it is like near only. It's like 6 days only you have. Okay, so just prepare well and just give the exam. Apart from this, if there is any doubt or anything like this, so just tell me that what is the feedback? Like, is the course good? You have learned new things, or is there any like a scope of like, or there is a scope, or there is always a scope that we can have better understanding, or we can give you better methods to understand the topics. So any feedback like you want an improvement in which section of the like teaching style or the material or the way of teaching, whatever. If there is any feedback, then you can give. This time there were very less number of people who joined the class actually. So it's quite demotivating for me also to teach in a like empty class many times. Okay, so if that is nothing, then we'll end this session. Okay, so yeah, you can just access all the material from the drive and the YouTube, and further just if there is any query before exam, then you just post it on the swam portal, and they'll just answer your queries there. I hope you just perform well in the exam. Okay, and all the best. We'll end the session now, I think. Okay, so Okay. So I'll stop the recording and you may leave now. Thank you for joining. Thank you for having patience for like a long time. Yeah.